Are you worried about global warming? Concerned about power outages? Struggling to pay bills? Or do you just like staring at spinning things? Nine Wind has the right solution for you. Our company designs and manufactures excellent quality small horizontal axis wind turbines with very particular design limits. The turbine is made out of ABS plastic for blades and cone and aluminium for the hub. It rotates clockwise, its diameter cannot exceed 400 mm and the mass is kept below 400 grams. Its maximum angular velocity should not exceed 3000 rpm. It has to self-start at 10 meters per second and should reach the maximum pressure power coefficient, which is the ratio of power delivered by the turbine to maximum available power, at tip speed ratio between 3 and 8. Our design process focused on aerodynamic properties of the turbine first. Our engineers started by researching available literature to develop the preliminary design taking into account appropriate airflow profiles, chord and twist distribution, and cone shape. Simulations were run in X-Fall and Q-Blade in order to fine-tune the initial ideas to specific design requirements.
After intensive research, we settled for two airfoil profiles, SG6043 and SG6040, very popular choices for small wind turbines. The former provides good lift-to-drag ratio, while the latter ensures good structural properties near the root of the wing. The optimal transition point was found to be at approximately 6 centimeters from the root. Angles of attack were chosen to be 7.75 and 9 degrees respectively, in order to produce as much lift as possible without stalling. The variation of chord along the wing was calculated using the Betz approach, while the twist of the wing was calculated using the Schmitz approach to ensure the optimal angle of attack was maintained along the blade. Finally, we designed the shape of the cone using the optimum fineness ratio. The aim here was to ensure the flow leads smoothly without reducing the lift near the root. After this stage, analysis of structural properties is required. We must take into account the loads associated with centrifugal, force, lift and drag. We then compare the resulting stresses with the ultimate tensile strength ABS plastic.
Allora, stavamo dicendo che dopo aver fatto
Daniel? English!
Oh god, I'm sorry guys. A structural analysis was carried out in order to determine whether the blades would withstand the aerodynamic loads. The blade was discretized into 200 smaller pieces, for which lift, drag and centrifugal force were calculated using a MATLAB script. The resulting stresses were then compared with the ultimate tensile strength of ABS plastic. We found that the combined stresses didn't exceed 11% of the ultimate tensile strength at any point of the blade. The highest stresses, due to the centrifugal force, occurred at the root, while the highest stresses, due to lift, were found to occur at the tip. Satisfied with this result, we carry on to analyze the maximum possible deflection at the tip of the blade. The blade was again discretized into 200 smaller pieces, and using the engineering we found that the maximum possible deflection was 1.6 mm, which was really reasonable.
The blade was idealized as a simple beam fixed at one end and free at the other. The polygon area formula was then used as a function of chord length and airfoil profile to estimate the cross-sectional areas across the 200 sections of the idealized blade. This enabled us to model the beam's flexural stiffness, EI, as a function of the chord length. After that, the lift, drag and centrifugal force distributions and approximations provided by the aerodynamics department were used by the structures department to find and analyze the bending moment and displacement distributions. This was done in parallel to a Creo simulation for comparison and verification.
For the aluminium hub, we decided to go for a hexagonal shape with a slight interference fit to make sure it stays in place. As aluminium is a relatively strong material, our main consideration was reducing the mass. In order to do so, the hub was designed with 15 holes on its faces. Of course, we also had to make sure that the design fits the test rig described in the project brief. The turbine concept was then made into a CAD model using Creo Parametric. After checking the possibility of manufacture with the workshop, we decided to add some additional material at the trailing edge of the blades, so that the 3D printer doesn't have problems printing the sharp edge. The CAD model was then sent to the workshop, along with drawings for the manufacture of the hub. The expected weight of the turbine was 110 grams.
In order to manufacture the aluminum hub,
Aluminium.
a cylindrical piece was smoothened at its face and reduced in diameter using a lathe. This gave a generic shape to work down into our hexagonal design. The central hole was drilled along the center line of the cylinder, gradually increasing its diameter and making sure it matched the tolerance of the shaft. The piece was then cut to size and taken to our milling machine, where the outer side of the cylinder was cut into a hexagon. Having obtained our desired design, some weight-reducing holes were drilled into the hub. Finally, we threaded in the grub screw hole and added the keyway needed to attach the turbine to the testing rig. The blades and the cone, however, were 3D printed in blue ABS plastic. We had to get rid of some excess material on the trailing edges and level off the originally rough surface. Sanding down the trailing edge proved to be quite a challenge and required a lot of work. However, we were rather pleased with the final result. The surface of the blades and the cone was gradually smoothed down using finer and finer grained sandpaper to ensure the attached airflow over the turbine. This would prevent turbulence, which would make the performance worse.
The Donald Campbell wind tunnel. When our product was ready for testing, it was transported to the Donald Campbell wind tunnel at Imperial College London, where it was reweighed and remeasured for accuracy. The testing rig at Imperial College was made up of a 16mm diameter shaft connected to a torque transducer and hydraulic brake. The objective was to generate as much power as possible at wind speeds of 6, 8, 10 and 12 meters per second, and have the turbine self-start at 10 meters per second. The wind speed in the tunnel was brought up to around 15 meters per second, and after giving it a push, the wind turbine finally started. The speed was brought down to 8 meters per second, and up to 10 meters per second and 12 meters per second. After realizing that our turbine resisted stall, we took the speed down to 6 meters per second and managed to get some power out of it, around 1.5 watts. After that, we attempted to capture the actual self-start speed and found that it started at around 17 to 18 meters per second. The summarized testing results are presented in the table along with the power curves. Even though the turbine managed to produce a maximum power of 20 watts at the highest wind speed, the results did not entirely match our predictions. We expected the maximum CP to be around 0.55 as compared to the actual maximum of 0.17. Being an ambitious company, we always strive for improvement of our products. Following the testing, we identified key areas which would improve the performance of our wind turbine, eliminating theoretical infinite stresses and strengthening the root by introducing an elliptical blade cross-section at the root and blending the blade with the cone. Our results showed that making an aerodynamic and power-efficient small wind turbine required either a third blade or some sort of self-starting mechanism, as average wind speeds in our studied target locations were nowhere near that required to self-start. Turbine efficiency could have been increased by reducing its mass by designing a shorter and lighter hub in addition to a shorter and hollowed out cone. Also, having a hollow blade with internal vanes that withstand stresses throughout the blade could have provided an equally strong but much lighter turbine. Making full use of the current capabilities of 3D printers and removing the extra material from the trailing edge could have given us more time to smoothen the surface of the blade and the cone. Also, a layer of paint could have been applied before testing. We also believe that a larger diameter would have allowed the blade to self-start.
In short, our turbine is ideal for households in rather windy areas, although you might need to give it a bit of a push. It can power equipment such as 2 routers, a DVD recorder, 2 table fans, or a PS4 on standby. Contact our offices in London, Rome, Warsaw, and Damascus, and say goodbye to power outages and enormous electricity bills.